did everything by hands. So they needed a simple model. It is simpler to estimate only one value of river flow instead of the whole hydrograph. It's simpler. And also this is what they needed, because they wanted to get protected against floods. They needed to know the max. Okay, so the rational formula is very simple. It says that the peak flow is equal to the product of a coefficient that we will discuss later times a representative value of rainfall times the area of the catchment. A representative value of rainfall is an intensity. C is a coefficient that is adimensional. Okay, if we analyze the units of this relationship, the peak flow is length to the power of 3, it's a volume, divided by time. Remember, volume of water per unit time, this is the definition of river flow. Okay, which is equal to C is adimensional, so nothing to add here. Rainfall intensity. Rainfall is usually measured as a length. It's rainfall depth. So we say today it rained 10 millimeters of rain, which means a length. Intensity, it means length over time. Area is L squared, which is fine. It's dimensionally consistent. Keep in mind, when you talk about rainfall, you can talk about rainfall or rainfall intensity. Rainfall is a length. Rainfall intensity is a length divided by time. So we make a difference between the two. So we say a rain of 1 meter or a rain intensity of 1 meter per year. Actually, what I would like to emphasize is that when we talk about rainfall, it's meaningless to talk only about rainfall. We always have to refer to a duration. And therefore, I would say that we have always to refer to an intensity. Because it is meaningless if I just say a rain of 1 meter. In what time? I have to say how long it took to rain 1 meter. And therefore, keep it in mind, because when you make your computations as an engineer, of course you need to make sure that units are consistent. And this is tricky, because usually we measure rainfall in millimeters, and we measure the river flow in cubic meters per second or liters per second. So you have to be very careful in the units of the variable when you apply these estimation models, these engineering models. So you have to always take into account that you may make a mistake. Fortunately, usually the mistake means an error of 1 order of magnitude, so you realize it. But still you have to be very careful. And this is why I tell you, keep in mind that, let's say that rainfall is always associated to a duration. And this is tricky, because you get the data from the hydrographic service, and they tell you that today it rained, or you get an information that is January 1st, 1900, the rainfall height was 10 millimeters. And therefore you may use this number by taking as unit millimeters. It's not millimeters, it's millimeters per day. And you have to be always fully aware of that. Because day is one thing, second is another thing. So if I want the river flow in cubic meters per second, and I use the rainfall in millimeters per day, I have to make a conversion. And be careful because, as I said, there is a positive side that the mistake usually is easily detectable. But be careful because when you work with technical units, to be fully aware of what units mean. Okay, so I said that this is a coefficient. This coefficient is called runoff coefficient. It's usually comprised between, in the range 0, 1, 0 minor, so it's reductive. It's I'm not sure if it is correct to say reductive in English, but anyway, it is reducing the river flow with respect to the product of rainfall intensity times catchment area. If you think of the rational formula, it is very simple because basically what the rational formula says, it says I take the rain falling over a catchment, which is a volume of water at the end of the story, because it's a length over an area, so it's volume per unit time. And I estimate this volume of water that falls over the catchment by multiplying the rainfall intensity times the area of the catchment. And I equate this volume of water per unit time to the river flow. Given that I understand that not all the rainfall is converted into river flow because there is some infiltration, there is some evapotranspiration, then I introduce a coefficient that is between 0 and 1. Okay, so what is this equation? It's a mass balance equation. This is something that you don't find on the books, but actually when you equate the volume of water that falls over the catchment to the volume of water that flows into the river, you are simply applying a mass balance equation. It is very trivial. And it is just enough, because you have only one unknown. You are not taking into account the state of the catchment. Or, actually, you are taking into account it implicitly through the coefficient C. C takes into account infiltration and cover, evapotranspiration, temperature, wetness, dryness of the catchment in a static way. Usually it is assumed to be fixed. And basically it is an empirical way of removing energy balance. So you are not concerned about energy balance here, you neglect it, you just apply mass balance because it is simple. This is called an empirical model, but you see that it's indeed empirical, but we can easily associate to this empirical relationship a physical meaning. It's a mass balance equation, energy balance is neglected, and it's embedded implicitly in the coefficient C. Also, implicitly it's also embedded in other assumptions of this model, which we will discuss soon. Of course, you need to find a representative value of rainfall. This model is highly sensitive to each one of these variables, of these multipliers. In particular, it is sensitive to the representative value of rainfall. And it could be an observed value. You may apply this formula to reproduce the river flow after an observed rainfall. But actually, given that it's a formula that is it's conceived to provide an estimate of a flood flow, we should use there a rainfall value that corresponds to a flood. So we should use the rainfall amount that typically produces floods in a catchment, which is something that is related to the catchment itself. Like, for instance, if you think a very large catchment like the Po River, typically the Po River, floods in the Po River are originated in the fall season by long rainfall with low intensity. Keep in mind that duration of a rainfall event is related to rainfall intensity. This is something that is part of your background in hydrology. If you have a long rainfall, the intensity is low. And if you think at your intuition, when you have rain like this week, lasting for 1 week, it's not a rain like that. If you get into the rain in 30 seconds, you are completely wet. It's a low intensity rain. Instead, your experience tells you that during summer it may happen that you get storms that last for 1 minute, but during that minute you get completely wet. It means very high intensity, and typically very high intensity is associated with short rainfall. So, Po River gets floods when the rainfall is long and low intensity. Conversely, if you think about sewers into the street, their catchment is very small. Typically they get overflowed by short rainfall with high intensity. So you understand that the representative value of rainfall, meaning that it's the rainfall that induces floods, is different in different catchments. So we have to introduce here a rainfall with the proper duration. And to the proper duration, depending on meteorology, corresponds an intensity. Meteorology tells us, if we specify rainfall duration for a location, meteorology tells us, also engineering, hydrology, tells us what is the corresponding intensity. Okay, so one last thing that I would like to say about this model, about the rational formula, is that it can be proved that the critical rainfall, meaning that the rainfall that induces for a given catchment the worst conditions in terms of flooding, so it can be proved that the critical rainfall has a well-defined duration. And this under certain assumptions. I don't want to go into the details. You'll find in my web pages the links to follow if you want to better inspect this. So, what is the duration that corresponds to the duration of rainfall that corresponds to the critical flood? The duration is equivalent to the time of concentration of the catchment. And now I have another definition to provide. And also this is the reason why I wanted to introduce this concept of critical rainfall, because it gives to me the opportunity to introduce the time of concentration. So what is the time of concentration? Time of concentration of a catchment. In Italian it's called the tempo di corrivazione. What is the time of concentration? Okay, take the closure section and identify the point in the catchment that is the I don't know how to say in English, but it's located most far from the closure. I'm not sure whether I can say farthest, but I think you understood. The point that is in the catchment is located most far from the closure. closure. I would say that it could be in this case this point here. Let me take another color. Or this one here. We say that we take the point that is hydrologically more far from the closure. Hydrologically means the point such that a drop of water falling there takes the longest time to get to the closure. So the point such that the drop of water that falls there takes the longest time to reach the closure. So we call this longest time to reach the closure time of concentration. So we can prove, as I said, under certain assumptions, I am repeating, that the critical rainfall, so the rainfall that induces the most critical conditions in terms of peak flow, is induced by an event that has a duration that is equivalent to the time of concentration. This is important because it gives to you a tool to evaluate with respect to a catchment what is the duration of the rainfall event that induces flooding conditions. The Po River, what is the time of concentration of the Po River? Okay, keep into account that the Po River from Piacenza to the sea takes about 2 days. So the time of concentration of the Po River may be, if you go back to the Alps, 4 or 5 days. Indeed, it is true that the Po River gets floods if the duration of rainfall is longer, it's about 1 week. If you think about sewers into the street, the time of concentration is about 2 minutes, because the catchment is very small and it's impervious. So the time of concentration is 2-5 minutes. Indeed, we know that the storms that cause overflow of sewers, it's about a duration of 5 minutes. So, when you look at a catchment, based on your experience, you can estimate time of concentration, and then you get an idea of the duration of rainfall that may induce critical conditions. I think this is important. Okay, but I said that the rational formula is not much used in water resources management, because in water resources management, we need to reproduce the whole hydrograph. We are not interested in only the peak. And also in water resources management, we are interested in low flows more than in peak flows, because typically when we have the peaks, we cannot use all that water. We can use it only if we build a dam and then store it. But in normal situations, unless we have the opportunity of building a dam, we are not interested in the peak. Because when the peak flow passes, we cannot get all that water. We are interested in the low flows, and the rational formula is not useful for describing low flows at all. Keep in mind that in general, describing low flows is much more difficult, and also to observe them is much more difficult than dealing with peak flows. Think about a river when there is the low flow. Typically, the river gets braided, splits into several branches, and we say braided river. And to estimate the flow, it's really difficult because you have to go on one branch and then the other branch, and the velocity is so small, the velocity of water, and it's difficult to measure it. Instead, observing a flood is easier. Okay? Now, given that we don't use the rational formula, let me introduce another model, another mathematical model that we can use for water resources management. And the second model that we can introduce, which is very well known, it's the linear reservoir. The linear reservoir, it's a model that is based on a conceptual scheme that is identical to what was drawn into this blackboard before. I am redrawing it. The linear reservoir assimilates the catchment to a bucket or a tank. And assumes that we have a rainfall falling into this bucket and river flow that is assumed to originate from a bottom discharge. Can I please ask you to raise your hand if you already know the linear reservoir? Okay, 4, 5, 6. Okay, good. The linear reservoir, basically, it's very simple and applies the mass balance to this reservoir, but first introduces a state variable that is the storage. In differential terms, it can be written the mass balance equation in this way. The change along time of the storage is equal to rainfall minus river flow. This is a differential equation. Now, the problem is that I have two unknowns here, so I have to introduce another equation. And the assumption of the linear reservoir is very simple. Given that we have two unknowns, W and Q, the idea is to introduce a linear relationship between these two unknowns. If you relate one unknown to the other, you reduce the number of unknowns, because once that you know the first unknown, through the relationship that you assumed, can compute the second unknown. So it's very simple. The idea is, let me reduce the number of unknowns by assuming a linear relationship between the two unknowns. And therefore what I do is simply to say that Qt is equal to Wt divided by a constant K, which has the dimension of a time. It's the unit is time. Okay, very simple idea, but this idea, I want to explain it with a physical reasoning, because the idea is very empirical, it's strictly mathematical. We are engineers, let's find a physical interpretation. The physical interpretation is very simple. Once that you establish a relationship between outflow from this bucket and its water content, you are basically saying that if you increase the water content, you have more outflow. And what is the reason why you have more outflow in this bucket if you increase the water content? Because you have more pressure on the bottom and therefore more water that comes out. More pressure, why you have more pressure? Because there is more potential energy that is converted into kinetic energy in form of flow. So basically it's a conservation of energy. And in fact, you know from Torricelli's law, fluid mechanics, I'm not repeating it, Torricelli's law, it's a physical law that allows you to compute the outflow from a bucket, from a bottom hole, depending on the water content into the bucket, and it is obtained by equating the potential energy of the water content and the kinetic energy of the river flow, of the flow. And therefore, we know that indeed a relationship between W and Q can be derived rigorously by applying energy balance. Energy balance, potential energy, kinetic energy. We know that. And there is a link on my pages to the Wikipedia page explaining the Torricelli's law. It's an energy balance. Actually, Torricelli's law tells us that the relationship between Q and W is not linear. While here we are assuming a linear relationship. Linear means that you can draw it along a straight line. Instead, Torricelli's law says that the relationship is not linear, so basically there is an underlying assumption that is introduced. Why they introduced, when they proposed this model, why they assumed that the relationship is linear, why they knew that it's not? Why did they adopt this assumption? The explanation is extremely simple. Because if you assume that the relationship is linear, the model becomes simpler, simpler and simpler. And you can apply it through hand computation. Instead, if you introduce non-linearity here, it becomes impossible to analytically integrate this system of equations. Okay. This is a system of equations that suffices two unknowns, two equations. We are done. Now, there is one thing that I want to tell you about a general philosophical consideration. I suspect that you, as I was and still am, you get concerned when you see a differential equation. Because we are not mathematicians, we are engineers, and therefore integrals and derivatives typically concern us. Okay, the sense of my message is, even in this case, get free by this concern. The differential equation, it is a normal equation that instead of describing the variables directly, describes the increments, the differences, in time. So in this case, this equation doesn't describe W. It describes the difference in W between one day and the next day, for instance. That's it. And it only means that if you want to compute W, you have to sum these differences. And the summation is nothing else than an integral. So you don't have to be concerned by we don't have to be concerned by differential equation. With the PC, we can solve it very easily. We just have to make sure that we apply the equation in the right way, we compute the differences, the increments, and then we sum them. In the PC, it's extremely simple. From an analytical point of view, it's a complication. With the PC, it's very simple. And also, given that this differential equation describes the increments, when we sum them, we need a starting point. We need to know the value of W at time 0 in order, starting from that point, to sum the increments. And this is called initial condition. That's it. You need an initial condition and you sum it up. And then in some cases you may have boundary conditions, but I don't want to go into the details. The message that I want to send to deliver to you is let's get free by this concept. Okay, that being said, given that this model is linear, it's possible to integrate it analytically. And given that you already explored the linear reservoir, you already have the means to understand how to compute this integral. And this is explained in my pages. There are all the steps. Here they are. Okay, look at the upper part of the screen. Basically, we start from these two equations. You see the equations up there are the same that are described there. And then we incorporate the two equations into one. And it's the equation that you see up there. And then we can integrate. And the integral can be, this is the result of the integral, which is, note that the result that you see in the upper part of the screen is still an integral, because we can solve only part of them. In order to completely solve it, we need to specify p tau. We need to give a function for rain. If we don't give a function for rain, we cannot completely solve that integral. So the final general solution of the linear reservoir still includes an integral. But if we assume that rain is constant, we can easily integrate it, getting this final solution. Okay, I leave to you the job of studying this, how this integral is computed. Please keep into account that this is a typical question at the exam. And if I teach it, it will take about 15 minutes. I think, given that you already, most of you already know about this, I think it's better if we start tomorrow, Monday, from the estimation of the parameter k, because this is something that I didn't talk about. We talk about it on Monday. But meanwhile, please have a look at the integral, and if you don't understand something, ask me, because as I said, this may be a question at the exam, like, okay, please, let's talk about the linear reservoir, what are the starting equations, and then you write down this equation, and then I say, if you can compute the integral, I would appreciate it. And of course, it means that if you can explain to me how to compute the integral, I appreciate it. And okay, for next week, then we will start from the estimation of k, and next Tuesday, please bring your PC, that I hope that we will be able in R to apply the linear reservoir. Okay, perfect. Thank you.